Okay, so because there is this activation function at the end which converts everything to binary, namely 0 or 1, all we are getting is this 0 or 1. This network has the potential to give you much more complex 0 1 switches if you pick the biases and weights sort of carefully. I've just chosen them to be random here, but essentially, if you pick them appropriately, you can have multiple switches between 0 and 1 in whatever range that you want. Okay. We're not necessarily seeing that, like I said, because these have just been chosen randomly. Um, okay, so, but let me show you a version of this network, a slightly simplified version of this network that actually shows the underlying complexity of the functions that could be approximated. Okay, um, let me basically comment out this line, which at the very final step transforms whatever we get into 0 or 1. Okay, so what we have is a neural network where we have a single input and then it goes to, I don't know, 200 neurons, um, and they do apply a linear transformation and then the nonlinearity, namely the binary activation function, and then all those things get transformed by a linear transformation here, and then that's it, and then you get the output. Okay, without a final step of converting that into 0 and 1. And let's see what this resulting function looks like. Okay, let me just run this thing. There's a bug apparently. Let me click on this line. Well, I suppose, yeah, I'm just saying that y layer 2 is just the same as z, essentially skipping the step. Let me save this, run it. Okay, so that's what you get. In the range -2 to 2, you get this incredibly noisy, complicated looking function. It looks like junk. It looks very noisy. But the point here, and that's just because we've used random weights and biases, but what this random looking function indicates is the sort of complexity of the ups and downs that you can potentially hope to approximate by appropriately choosing these biases and weights. Okay, um, if you chose the biases and weights appropriately, you could approximate a function that has like ups and down wiggles, as many ups and down wiggles as I guess there are these steps. Okay, um, what this activation binary step achieves is basically allows us to um, approximate uh, some function here using flat pieces. Okay, um, these bias terms essentially put these jumps at various points, and then the and then of course the weights provide some scaling up and down of the outputs. Uh, and by putting the bias terms at various places, namely the thresholds at various places, you can have these steps at various places. And what you can essentially do with the function like a neural network like this is essentially get piecewise constant functions. And of course, uh, if you have sufficiently many pieces of this piecewise constant function, um, and you're able to adjust the height of each of the pieces, you can approximate any function you want. Imagine any function, you can just draw little sort of flat um, pieces adjacent to every point on that function, and you sort of do a step-like approximation of the function, and you can make that step-like approximation arbitrarily close to the original function. And that really is the basis for the universal approximation theorem, that an activation function like this allows you to approximate the function using piecewise constant functions, and piecewise constant functions can approximate any function really, um, at least a function value. Similarly, if you have ReLU activation, you would be approximating um, a function using piecewise linear pieces, and you can again approximate any function, in fact, better using piecewise linear pieces. Okay, so that's the idea that if you have 200 neurons, you get complex functions like this. Let me reduce the number of neurons here. Let me make it 20, run it. If you have 20, then all you get are, well, a few jumps. If you have 200, of course, you have many more jumps and much more complexity. If you have 2000 neurons, you get potentially the possibility of approximating incredibly fine features. This looks like noise, but then by tweaking all those little um, um, uh, peaks and valleys and tune them in a manner that approximates a function, you can approximate anything you want. Is the idea. Okay. So let me stop this video there.